In this video, we're going to look at static error constants. And so what these static error constants are just parameters that we're using to help us specify our steady state error performance. So in that sense, we can say it's sort of similar to when we looked at our zeta, our damping ratio, and our omega n, and we use that to help us characterize our time response or our transient response of the system. So it's a similar idea to what we did with that. And so what we're going to do is we're going to define three different static error constants. So the first is our position constant. So our position constant is just going to be Kp, and it's equal to the limit as s goes to 0 of g of s. And so that should look very familiar because that was part of our equation when we looked at step inputs to our unity feedback system. So what that means then is if we have a step input to a unity feedback system, then what we can say is that our steady state error, E of infinity, is just equal to 1 divided by 1 plus our static error constant, Kp. So we get something that looks like that. So let me go ahead and copy this because we're going to say similar things for our next two. So the next static error constant is our velocity constant. And so our velocity constant is going to be k sub v, and this is equal to the limit as s goes to 0 of s times g of s. And so again, this should look familiar from when we were considering our ramp input. So now we can say here that if we have a ramp input, so let's just change that from step to ramp. So a ramp input to a unity feedback system is now going to give us a steady state error, E of infinity, which is equal to 1 divided by kV. So then our third static error constant that we're going to consider is our acceleration constant. So our acceleration constant, which is just going to be k sub a, and so this is equal to the limit as s goes to 0 of s squared g of s. And so again, this also looks familiar. Now we're talking about a unity feedback system with a parabolic input. So again, let's get rid of this step, and so let's replace that with parabolic. So if we have a parabolic input to a unity feedback system, now we can say that our steady state error, E of infinity, is equal to 1 divided by Ka. So what's the benefit of defining these static error constants? So as we can see, it gives us a quicker way to sort of characterize a system. So instead of just looking at the general G of S, we can now quickly say, oh, this system has a KV of such and such. So we know what to expect for various input types. And another thing that we can see for all three of these, so for our three sort of updated steady state error equations for our different input types, so we can see in all cases that our E of infinity is going to be decreasing as those static error constants are increasing. So all cases our E of infinity decreases as our static error constants increase. And so what that tells us is that in general, if we want a small steady state error, then we want to have a large static error constant because small steady state error corresponds to large static error constants. And so if you want to see some examples or get some practice with this, you can look at example 7.4, which is on page 281 of the 8th edition text. In the next video, we're going to come back and we're going to sort of put this idea together with our errors and our different types of inputs, and we're going to introduce this idea of system type, and then we're going to sort of move on from there. But hopefully that will sort of bring all of these ideas together.